second derivative test because the second derivative may be too difficult to compute. So it's possible, or to find the sign maybe. So I would say, okay, if there is a critical number here, the function must be, the second derivative must be negative. If the critical number is local max, how can this be the other way? It cannot. So if there is a local min, obviously the second derivative has to be positive because the function must look like this. So there are ways of using the second derivative test to check or conclude things about the second derivative. But I do not wait till I get to the second derivative to study the sign of the first derivative. I never do that. It's a matter of habit. I'm not saying it's good or bad. I'm just saying develop your own style. Okay, so what does the second derivative test say in short? The second derivative test says that if C is a critical number and f of x is greater than f double prime, if the second derivative is positive, then minimum. Again, if C is a critical number and the second derivative is negative, then C gives a max or creates a max. I'm just going to change this into greater than, just greater or less than. Okay. So now we know everything except graphing yet. We will. I just would like us to choose another function and go through all these steps, analyzing the table, filling out the table, and getting ready to graph. And then we will graph. Would you like to look at a rational function now? Would you like to look at an exponential? Would you like to look at a log function, exponential, rational? I always like to show as many different examples as possible.
Can we look at a function that just has an odd root in it?
That doesn't have what?
Like an odd exponent. Look at one that has an odd exponent in it.
You mean a polynomial function?
Well, yeah, like what would the difference be if it had like a polynomial function like had an odd
of odd degree? Okay. Exponent or degree?
Degree.
Okay, perfect. So 36x plus 3x squared minus 2x to the third. Is that what you had in mind?
Something like that.
Perfect. Very good. It's identical. I was hoping for a rational or something else, but if this is what you would like to see, I'm super happy.
Maybe we could do rational as well.
Oh yeah. No. Let's finish this one and then we'll choose a rational, of course. I get my table going. F prime, f of x, and the second derivative. It's a polynomial function, no restrictions on the domain whatsoever. Of course, 0 must be in the table and 0, 0, 0, 0. I will have to find the end behavior and the x-intercepts. And only then I move on to the first derivative. So limit as x approaches negative infinity. And I'm going to correctly write it as negative 2x to the third plus 3x squared plus 36x. And then the limit as x approaches infinity from negative 2x cubed plus 3x squared plus 36x. And then the x-intercepts. Can anyone tell us or give us these limits?
As x approaches negative infinity, y also approaches negative infinity, and as x approaches infinity, y approaches infinity.
So let's do this together. negative infinity to the third power is a negative number. That negative number multiplied by negative 2 will give us infinity, right? Agreed?
Yes.
Yes.
So infinity to the third will be positive, but there is a negative 2 in front, so that will be a negative infinity. So this is negative infinity. Final step. Let's find the x-intercepts. So when y equals 0, negative 2x cubed plus 3x squared plus 36x equals 0. And yes, I will multiply both sides by negative 1. I refuse to solve anything that has a negative leading coefficient. So 2x cubed minus 3x squared minus 36x equals 0. I will factor out x and I get 2x minus 2x squared minus 3x minus 36. And I'm not going to waste my time. And I'm not going to use a new calculator because I trust this one that is probably 20 some years old. So that has the poly feature too. I get 2, negative 3 and negative 36 and solve. And I got one solution that's, of course, one solution is x equals 0. The other one is x equals 5.06. And the other one is x equals negative 3.56. And I do trust this one. Okay, so I will put them in the table. When x is 0, y is 0, which we know, 5.06, 0. Negative 3.560. We exhausted the function. We cannot learn anything else about the function from the function itself. Done. Now we're ready to look at this first derivative. So f prime of x will be negative 6x squared plus 6x plus 36. No critical numbers come from f prime being undefined, but I have to say that. But f prime could be 0. Negative 6x squared plus 6x plus 36 equals 0. Of course, I'm going to divide by negative 6. And I get x squared minus x minus 6. There is no need to use the calculator because this is x minus 3 and x plus 2. Quite nice. X equals 3 and x equals negative 2. So these are critical numbers. I will go back to the table and punch them in. So let's see where we put in negative 2. Okay, I have some room for negative 2. Then I have to put in 3. The quadratic, first derivative is a quadratic function with a negative leading coefficient. So I know it has a maximum. So between solutions, it must be positive. Outside must be negative. Or just plug in 0. 0, 0, 0, positive. Plug in 10 and you'll see. I would recommend plug it in here with a negative in front though. Careful. And you will see it's negative. I'll catch my mistakes in a blink. Because if these two rows don't go well together, then I'll say, something is terribly wrong. Okay, so I'll have to plug in the function negative 2 and 3. And I am going to use the calculator for this one. I'm going to put in the function as negative 2x cubed. And then plus 3x squared. And then plus 36x. And I am going to punch in negative 2 and then 3. And for negative 2, I got negative 44. And for the other one, 81. Now this is the moment of truth. See if these two work well. If they don't, I'll say, well, I wasted some time. Have to go back and redo. So from positive infinity to 0, yes. From 0 to negative 44, yes, of course. From negative 4 to 0, yes, of course. From 0 to 81, yes. From 81 to 0, yes. From 0 to negative infinity, yes. I'm confident that these two work well together, and the sign of the derivative is in sync with the values that I determined for the y values or the function values. Now I have to discover what the second derivative has to say. And let's see what the second derivative has to say. I have to find the second derivative first, which is negative 12x and plus 6. And when I set this equal to 0, I get x equals 1/2. Okay, do I have room for 1/2? Not really. It's a linear function with a negative slope. It has to come from positive and go to negative. Or you plug in numbers, whatever you want to do. Obviously, this is an IP, but I don't have it yet. So I have to go back to the calculator and punch in 0.5. So 0.5, and I get 18.5. This is the IP. This is obviously a local min, and this is obviously a local max. We're going to graph this function. So now let's analyze the table a little bit more. That the second derivative works well with the first derivative. So let's do that. So the function opens up. There is a critical number at -2, and this is a local minimum. Yes, it makes sense. The function opens up. There is a critical number in that area, so this must be a local min. Perfect. Now, the function opens downward. There is a critical number there at 3 in that area between 1/2 and infinity. At 3 is a critical number. Obviously, it has to be a local max because the function looks like this. Good. The only thing that does not fit in my table is symmetry, but this function cannot be symmetric. If it crosses at this and crosses at this and crosses at 5, there is no symmetry here. But I have to write it because I have to show that I checked. F of x, not symmetric. Okay, now we are ready to put everything together. I don't care about anything but my table. Nothing else matters. And I think I'm on page 8, yes. Okay, I'll start with the points. Here are the points. Negative 3.56. So let's plan ahead. I have quite big numbers on the y-axis, 18.5, negative 44, 81. On the x-axis, I will use a different scale. On the y-axis, I will use a different scale because otherwise I will not be able to show the graph. So 1, 2, 3, 4, 5. A bigger scale, 1, 2, 3, 4, 5. But because I have to get to 81, I'm going to say 10, 20, 30, 40, 50, 60, 70, 80, and that will be my 81. And 10, 20, 30, 40, 50 for the negative 44. Okay, so negative 3.56, 1, 2, 3.56. Negative 2, comma, negative 44, 1, 2, 3, 4, so it's somewhere here. 0, comma, 0, fine. 1/2, comma, 18.5, 10, 20. 3, 1, 2, 3, comma 81. Okay, so I have 5.6. 1, 2, 3, 4, 5.6. Okay, so I have all my points plotted. So now I have to look everywhere. What do I mean by everywhere? Just literally everywhere. First derivative, second derivative, increasing, decreasing. So here's how I proceed. From positive infinity, it opens up, decreasing, decreasing till this point where it crosses. It's an x-intercept. Fine. It comes to a local minimum, which is at -2, -44. Opening upward. Now, all of a sudden at this point, because it's a local min, it will start increasing to the origin. Fine. Increasing to the origin. Then it continues to increase, still opening up. Continues to increase, still opening up till the inflection point. What inflection point? 1/2, 18.5. At this point, we'll change concavity, and it will continue forever, opening downward. Okay, so it increases. So it's an increasing situation between 1/2 and 3. 1, 2, 3. Opening downward. And then it will continue to decrease all the way, opening downward, crossing the x-axis at 5, blah, blah, blah. This is the graph of f of x. -2x cubed plus 3x squared plus 36x. Even if you graph this with the graphing calculator, as long as I know, this is a new invention, so maybe it gives the points of inflection, but as far as I know, the old ones do not. I can't speak for the new one just yet. Haven't checked. This is how we put everything together, and this is our first application of this, you know, in addition to the Rolle's theorem and the mean value theorem, but this is the first major application of this chapter. Being able to put everything together with the first derivative, the second derivative, and everything combined. If you don't summarize the information, I doubt that you will graph from the graphing calculator, which I'm not interested, to put everything together and graph it. Any questions on this? Any questions? Okay, now we're ready to move on to other types of functions. You can choose if you'd like to see rational, if you'd like to see exponential, if you'd like to see log, if you'd like to see trig. And then I would like to look at an example. So till you make up your mind, I'd like to look at an example like this. We always had these examples. Yeah, let's look at, we are given f prime of 0, which equals f prime of 2, which equals f prime of 4, which is 0. We are given that f prime of x is positive if x is less than 0 or 2 less than x less than 4. We are given that f prime of x is less than 0 if 0 less than x less than 2 or x greater than 4. The second derivative is positive if 1 less than x less than 3. Second derivative is negative if x less than 1 or x greater than 3. And we are asked to, given all this, graph an example of a function that fulfills the above. Of a function that fulfills the above conditions. We've done this in almost in each and every chapter so far. This is gibberish, right?